some references. I was asked last time about to give some references. I'll just write a few papers and books. So first I would suggest, so there is this classical book, so Delin, Milne, August, and She. It's called Hodge Cycles, Motives, and Shimura Varieties. And it contains several chapters. So we have been talking about the things that are presented in chapter 1 and a bit about chapter 2. And also some papers of Delin. Actually, so basically everything I have explained is contained in the papers of Delin. In particular, so there is a paper about Weyl conjecture for K3 surfaces that appeared before the proof of the general Weyl conjectures. So that's one paper of Delin. Another is Hodge theory, of course, part 2 in particular. Also there is one about Shimura varieties. So the title is long. So it's about Shimura varieties, the constructions, and so on. So I'll just write the beginning. So basically everything I have explained is in these references. So this is very classical. So these are old papers. I don't remember the years because I haven't copied the years, but it's quite old. And more recent developments. It is also interesting to have a look. There are many actually. There is a lot of literature. I would just suggest that if anybody wants, you should have a look at the ICM talk of Klingler. So Klingler. It's called, it's in the archive, Hodge theory between algebraicity and transcendence. And also references in this paper. So this would give this Klingler's talk will give a good overview of the new ideas that have appeared recently in Hodge theory, and what we have done so far should be enough to understand what he is writing there. Yeah. So I haven't talked about these new developments during these lectures, but what we have discussed is somehow should allow you to understand what was going on more recently. Okay, so that's just basic references. Somehow the central subject is so the Mumford-Tate group, and so these methods that Klingler uses are very much group theoretical. Yeah, so that's the central, really the central notion for everyone working in Hodge theory. So today I would rather switch to something else a little bit, but not really something else. But so as I have promised, I would like to show you the Kuga-Satake construction for Hyperkähler manifold. So I'll recall a little bit. I'm not sure that everybody here knows what a Hyperkähler manifold is. So the Kuga-Satake construction. So once again, so what is the idea of the construction? So why do we want it? We know that we have, so the basic example of a Hyperkähler manifold is a complex K3 surface. And we know that, so on the cohomology, second cohomology of a complex K3 surface, we have this Hodge structure, and generically the Mumford-Tate group is the orthogonal group. So the claim is that this Hodge structure is of abelian type. It is contained in the subcategory generated by abelian varieties when the K3 surface is projective. So when the Hodge structure is polarizable, in general it is contained in the subcategory generated by Hodge structures of complex tori. Yeah. So so it is abelian, and this is the construction that I want to explain. That is also classical. That's basically, I think, well, the construction originally is in the papers of Kuga and Satake, but Deligne explains it here, I think, in this paper. So this is classical, but now we know many more examples of Hyperkähler manifolds, and the construction works very well in general, so for all cohomology groups of Hyperkähler manifolds. So let's talk a little bit about Hyperkähler manifolds. So this X will be today a compact Hyperkähler manifold. Or as also known as irreducible holomorphic symplectic IHS manifold. What does this mean exactly? It means that X is a compact, yeah, so compact C infinity manifold, simply connected, and that carries a Hyperkähler metric. It's a Riemannian metric, so plus a Riemannian metric. And G, such that the holonomy of the Levy-Chvit connection is SPN. This nabla is the Levy-Chvit connection. SPN. Well, this is this compact form of the complex symplectic group. Or you can also describe it as the group of automorphisms of the quaternionic vector space that preserve the Hermitian scalar product. Quaternionic Hermitian scalar product. So this H is the algebra of quaternions, and this is the quaternionic Hermitian product. So if you have two vectors V and W, so this scalar product is the sum of Vi, Wi bar. V and W are quaternions. Vi and W are quaternions, and this V and W are vectors in this vector space. Yeah, so these are it's a compact group, and it commutes with the multiplication. Yeah, for example, if we consider multiplication from the left by the unit imaginary quaternions I, j, and k, the action commutes with such multiplication. And then by holonomy principle, we get complex structures on our Riemannian manifold, because so these are invariant. So commute means that they are invariant under the action of the holonomy group. And so we may construct the corresponding tensor fields on our manifold. So holonomy principle implies that there is I, j, k. So these tensor fields on the so these are endomorphisms, yeah, of T x. They are the square to -1, and they are parallel. Therefore, the complex structures, almost complex structures defined by this I, j, k, are integrable. So these are complex structures such that, well, they satisfy the quaternionic relations. And so we have a lot of complex structures on our manifold. Also, we have the symplectic form, well, because this is a subgroup of this complex symplectic group. Also, it preserves the symplectic form, and the corresponding tensor field is a holomorphic symplectic form. On our manifold X, well, actually for every complex structure, we have this holomorphic symplectic form. So that's why it is called the irreducible holomorphically symplectic. Yeah. So that's let's write this down. I guess actually okay. I will remove the references. So this is recorded, and I think that people can watch online who wanted to see the references. So if we fix the complex structure I, for example, so I will denote the complex manifold by xi. So this x, yeah, so the C-infinity manifold is fixed, and the complex structures vary in a family. So this is this complex manifold with complex structure I, and we have, again, by the holonomy principle, basically. So we have the symplectic form. So this is a section of the bundle of holomorphic two forms. The manifold is compact, so this is closed automatically and non-degenerate. So this is symplectic form. And also, from this condition that the holonomy group is equal, yeah, so it equals SPN. So this is maximal. Sometimes people write compact hyperkähler manifolds of maximal holonomy. It could be smaller, it could be inside SPN, and then we also would have all these structures. But since it is maximal, so then this sigma I is actually unique up to rescaling. So this is actually spanned by sigma I. What else? So since it is symplectic, we have, yeah, we can take the top exterior power of this symplectic form, and we'll get a holomorphic volume form. All right, so sigma I to the power n is a holomorphic volume form. In the sense that this holomorphic form, it's a section of the canonical band, and it nowhere vanishes. So the canonical bundle is trivial. Okay, so we have the one particular type of Calabi-Yau manifolds here. And the dimension, so because this is a symplectic, so this is a symplectic form, so the dimension of our manifold is even to n. All right, so what are the examples? So that's what we will need, I guess, to know about our manifolds. So they are also scalar. Yes, so I haven't mentioned this explicitly, but so here we have the metric, this Riemannian metric is actually Hermitian with respect to all of these complex structures, and since everything is preserved by the Levi-Civita connection, this is a Kelly metric actually with respect to any of the complex structures IJK. So we have compact Keller manifolds, so we have Hodge structures on the homology groups, as we have discussed basically in the first lecture. What are the examples? K3 surfaces, complex K3 surfaces. For example, the quartics in P3 that we have already seen before. So G S is a quartic in C P3, hypersurface of degree 4, right? So it is not obvious at all that this hypersurface carries a hypercalorimetric. With this holonomy group, this is a consequence of Calabi-Yau theorem. Because there is an alternative definition. We should, so we may consider the irreducible homomorphic symplectic manifold that is complex manifold simply connected and such that this space is spanned by a symplectic form, and then deduce that actually they carry hypercalorimetrics. So that's what is happening in the case of complex K3 surfaces. So that is how we see that they are hypercalar. It's difficult to construct a hypercalorimetric explicitly. Are the examples? Hilbert schemes of points on, so let's say this S is still a complex K3 surface. So then a Hilbert scheme of points on S, n points on S. Strictly speaking, this is a Hilbert scheme of length n subschemes of S. Right, so we consider the subschemes of dimension 0 of length n, meaning that they are somehow structure shift with the n-dimensional complex vector space. So these subschemes may be non-reduced. This means that the n tuples of points may collapse on the surface, and this will give somehow different subschemes with the same support. So if we consider all these Hilbert schemes, so then this will be a smooth complex manifold and actually an IHS manifold for any n. Then another family is when we start from an abelian surface, or more generally, well, maybe better to say C2 over lambda, not necessarily a projective abelian surface, just complex, compact complex torus. And then also we can consider this Hilbert scheme on of subschemes of length n plus 1, for example, on A. But then this is not simply connected. So there is the Albanese map from here back into this abelian, the complex torus. And then the fiber is called a generalized Kuma variety. Sorry? Double cover of what? I don't think so. Never mind. So the so that the no, I don't have to take any covers. So the fiber is called the generalized Kummer variety. Also IHS. So this X here. So this is X, and this X is IHS. This one is also IHS. So this gives you two infinite families of hyperkähler manifolds, and also there are two exceptional examples in dimension 6 and 10. So constructed by O'Grady, exceptional examples of dimension 6 and 10. And also there are lots of examples of singular hyperkähler manifolds, or rather singular reducible holomorphically symplectic varieties that are also quite similar, but that's a different subject. So in this example, so what can we say about the cohomology, or well, in general, for a compact hyperkähler manifold? What can we say about the cohomology? So I'll briefly give you also an overview, because it's a rich theory. So the cohomology of an IHS manifold. Yeah. So let's talk a little bit about the structure of the cohomology ring. Yeah, I think so. As far as I'm aware, people have not yet succeeded, although they're trying hard, but don't think that there is any new example so far.
But if you drop compactness, there are many, right?
Oh yeah, if you drop compactness, then there are lots of examples apart from this. Well, the cohomology of an IHS X, a manifold X. Well, we have H2, first of all. Well, it's simply connected, so H1 is not there, so H1 is 0. Then we have H2. Well, let's put rational coefficients here. So this is, in fact, a K3 type Hodge structure. So let me try to explain what I mean by this. So a K3 type Hodge structure. So first, in the Hodge decomposition, we have H20. The Hodge numbers. So H20 and H02 are equal to 1 because of the condition that is written here. Yeah. So the space is spanned by the symplectic form. Let me just consider this fixed complex structure I, and let me not write this I all the time. So I'm assuming that I fix one complex structure in this hyperkähler family. These are the Hodge numbers with respect to the complex structure of hyperkähler type. Also, we have this H11, which can be, it is different from the Hodge number of a K3 surface, but still the shape of the Hodge structure is similar. And you remember that if this condition holds, and we have seen that on the Mumford-Tate group or on the Hodge group, we have this Hodge structure which has only 3 pieces in the Hodge decomposition, which means that this Hodge structure is kind of similar to Hodge structure of an abelian variety. So to tell you more, so I need to somehow, so on a K3 surface, we have the intersection pairing, which actually gives you a polarization, and also it's a quadratic form. Yeah? So we know that the Mumford-Tate group, for example, or the Hodge group is contained in the orthogonal group with respect to this quadratic form. And similar thing holds for an arbitrary IHS manifold. So there is the following statement. So it's Bavil, Bogomolov, Fujiki. the claim is that there exists a similar quadratic form for x. But what does it mean, similar? So, so the claim is as follows. So there is a constant, a rational constant, and a quadratic form. So let me write V, briefly denote this space by V. And Q, which is the symmetric bilinear form on the dual, such well, of signature. So let me write of signature 3b2 of x minus 3. Yeah, so this the dimension of this vector space is b2. So we have 3 positive directions and b2 minus 3 negative, exactly like for the K3 surface. So that's the same thing as the intersection product on a K3 surface. So this quadratic form has the following property. So of signature and such that for any cohomology class A, there is the following relation. So I will put here the integral. Well, A is of degree 2. Yeah. So the complex dimension of my manifold is 2n. So A to the power 2n will be of degree 4n in the top degree cohomology. So I can find this integral. And then this will be equal to Cx times Q of A to the power n. Okay? So this is called Fujiki relation. Yeah, well, there is a few technicalities here, but they're not so important. So this integral is just the pairing with the fundamental class. So how do I choose the fundamental class? Because to choose to define the fundamental class, I need an orientation. So so this is pairing with the fundamental class defined by the orientation given by the complex structure I. You may ask how, if I choose another complex structure in this hyperkähler family or any other hyperkähler metric, maybe the orientation will change. So in fact, it will not. So there is some canonical orientation on any manifold of this type that we are considering. And this is the pairing with the fundamental class. So this is well defined, and this is a purely topological thing here. So this does not depend on anything. So I just claim that somehow there is one fixed orientation, yeah, okay? And then that's just the intersection product in cohomology. It's a purely topological quantity. It's a polynomial of degree 2n on this vector space. And then the claim is that this polynomial happens to be the nth power of a quadratic form. Okay, so that's a property actually of the cohomology ring of this manifold. Yeah, and so this has a lot of yeah. So the form. So let me just mention. So this Q is called the BBF form. Yeah, Bavil-Bogomolov-Fujiki. Q is the BBF form. And let us just somehow remember this relation. Yeah, so Fujiki relations. Yeah, so the idea is somehow I have this polynomial of degree 2n, and it happens to be the nth power of a quadratic form, because later this relation somehow will appear again in a bit different way. So what else can we say about this form? So just list some properties that I will rely on. So just the same way as for a K3 source. So you may imagine that this just replaces the intersection pairing on the H2 of a K3 surface. So for example, the Hodge decomposition is Q orthogonal. And actually, well, let me just better write as follows. So just the Hodge structure on H2 is given by, well, as we know, that it is given by some representation of the circle in the GL of V. But actually, here it goes to SO of V tensor R with this quadratic form Q. Actually, so from this, it also follows that the Hodge decomposition is orthogonal with respect to Q. And the Hodge group is contained in the orthogonal group, again, like for the K3 surfaces. Also, well, if we have polarization on our manifold, so if, if omega is a Kähler form, on X, then Q of the class of this omega is positive always. So the orthogonal complement will have signature 2b2 minus 3. Yeah, and actually, if this omega happens to be also the C1 of an ample bundle, or that so that if the class of omega, we may say, belongs to H2 of XQ, then actually the primitive Hodge structure is polarized by this quadratic form. So then H2 of XQ primitive. So if the class of omega is rational, yeah, then this primitive subspace, or you may define it as the orthogonal complement to the class of omega, actually. And this will be polarized, is polarized by Q. Okay, so we have our Hodge group. It's a subgroup of the orthogonal group now. Remember at the first lecture, we have been talking about the action of the SL2 on the cohomology. So we might now use this omega and define the Lefschetz operators. Yeah, so we have the operator of exterior or the cup product with the class of omega and the dual operator. And we know that they generate a subalgebra isomorphic to SL2. So in this case, let us consider, now, yeah, well, let's just recall the notation. So this omega is scalar, implies that we have Lefschetz operators. Lefschetz triple, which is just the multiplication, or well, let's better write as a cup product into homology. So then the dual of the Lefschetz operator and their bracket L and lambda. I think I denoted it by theta, and this is this operator defines the grading. Yeah. So the three operators span a subalgebra isomorphic to SL2, and then we looked at the homology ring as a representation of this SL2. So here, actually, for the hyperkähler manifolds, we can actually construct a bigger algebra that acts on the cohomology. In fact, actually, you can construct this algebra for any manifold. What we can do for the hyperkähler manifold, what is better in the case of hyperkähler manifolds, is that we have an explicit description of this subalgebra. So you may define the following thing. You may now vary your Kähler form. So you may deform, well, you may consider arbitrary Kähler metric and generate a subalgebra by all such operators, yeah, for all Kähler forms. Also, you can deform the complex structure on your manifold. and somehow generate the the smallest subalgebra inside the endomorphisms. Yeah, so consider L omega and lambda omega for all Keller forms on all deformations of this complex manifold for this complex structure I. And then there is an explicit description of the algebra that they span. So what is the smallest subalgebra? So the smallest subalgebra, Lie subalgebra of the endomorphisms of H dot X. Well, if we just do this for arbitrary forms, let's say R, yeah, but that contains all such Lefschetz triples. Yeah, so that is the question. So here is the description. In this case, in the case of a Keller manifold, I will write down this algebra. There is, so first let's introduce some Mukai extension of this quadratic vector space, VQ. I have the vector space here with the quadratic form. So I will define V tilde. This will be V plus U, where U is the hyperbolic plane. The quadratic form on the hyperbolic plane is this, given by this matrix. And the Q tilde will be Q plus this quadratic form of the hyperbolic plane. And also I want to introduce the grading here. So this V was of degree 2 kind of, and so the hyperbolic plane, so this as a vector space, it is 2-dimensional. So I want to place one isotropic generator of this vector space in degree 0 and the other in degree 4. Grading V tilde. So this will be Q plus V plus Q. So this is in degree 0, in degree 2, and this is in degree 4. So this, well, let's, I guess, yeah, so let me denote the generators by E0 and E4. And then I have the Lie algebra, the orthogonal Lie algebra of this extension, Mukai extension. If we think about it as lambda 2 V tilde, yeah, so then this will have the following degrees. So lambda 2 of this vector space. So so this is 1-dimensional. So we have a component of degree -2, which is basically E0 of HV, plus there is a component of degree 0, which is lambda 2 V plus E0 of HE4. So this is of degree -2, this is of degree 0, and there is a component of degree 2, E4 of HV.
So your V is -2.
Yeah, 0, 2, and 4. You may place -2, 0, 2, it doesn't matter. Yeah, because when you consider the endomorphisms, so these are the endomorphisms that somehow decrease the degree. Yeah, so these are that are preserve the degree, and those are that increase the degree. So what are those endomorphs actually? So those are just these guys. Okay, so the Lefschetz operators and the dual Lefschetz operators. So this lambda omega, it lives here. And the L omega, it lives here. Okay? And their brackets are contained here. So, yeah, so now the theorem is that actually, so this is the minimal Lie subalgebra that contains all these Lefschetz operators. Okay, so, I guess this is so Misha and Luyenga-Lunz, Misha Verbitsky, so theorem, Verbitsky, Luyenga-Lunz. Well, this subalgebra, so that this subalgebra, let me just denote this by star. So this subalgebra star is isomorphic to SO V tilde Q tilde. Okay, so now, so since we have this subalgebra in the morphisms of our cohomology ring, yeah. So and we have this, yeah, the degree decomposition. So we have some components of degree -2 and 2. So actually, so here the comment is that actually the difference between the hyperkähler case and the general case, because you can, you may choose any manifold, whatever manifold you want, and define the same thing, because there is nothing special here about hyperkähler manifolds. You may define this subalgebra, but then it's not actually, the problem is that it's very difficult to describe, so it will be somehow much bigger and less controllable. It's not even clear in which degrees this subalgebra will be concentrated. So this is quite remarkable, actually, that this algebra here in the hyperkähler case, it has only degrees -2, 0, and 2. Yeah.
In general, you have to construct the third iterate, right? In general, you construct the third one, and you have the one which this is just multiplication by the form. The central one, and the third one, and this is sort of Jacobson-Morozov thing, right?
Yeah, so this one, right? So this one is the third one, right? Yeah. So this bracket is also contained here, right? But still, so the problem here is that you don't know, for example, that the dual Lefschetz operators for different Kähler forms that they commute, for example. So there might be something in degrees smaller than -2 and bigger than 2. Okay, so now we know this, that we have this. So we have the action of this algebra, yeah, on our homology. Well, it's clear how it acts. So there are these Lefschetz and dual Lefschetz that they sit here and there. And there is also this piece. So this is, of course, isomorphic to SOV, well, the orthogonal algebra of the vector space V, so of H2 itself. So we have an action of SOVQ on, on HK, yeah, on HK of X. Well, this is, the algebra, I must emphasize, this is rational. So this is, everything is defined over Q. So we have this action of this guy, because it is of degree 0, it acts on every cohomology for every K, fixing the degree. Actually, the Hodge structures. If we have this action of the orthogonal Lie algebra, well, we may integrate it. So it becomes a representation of the spin group in general. HK is a representation of the spin group. Yeah, well, for any k. For even k, the representation will actually go through the orthogonal group. So for k even of SO VQ, so that the kernel of this double covering from spin to SO will act trivially on H k with even k. And the claim is, so that is in addition to what is written here, yeah, so that actually the complex structures and the so the Hodge decomposition, yeah, so we have the Hodge decomposition on the cohomology groups, that it is induced just by some morphism, so the Hodge structures on HK are induced by some representation. So from U1 to this spin group. So there is just one such representation that determines the Hodge structure on all cohomology groups. And then, of course, you see, well, for even k, it factors through SO. So the Hodge group, actually, of all these HKs, it is, well, the minimal subgroup that contains the image. So this should be over R. Yeah. So this is V times R. So the minimal rational subgroup that contains the image, and it is essentially the same for all somehow for all even cohomologies. It is the same, and for all odd cohomologies, it is just the subgroup of this spin group. So to control the Hodge structures, we need to view our. It is enough somehow to understand the structure of the cohomology ring as a representation of this algebra, essentially. Now, well, the question is, well, let's recall the notation. So we have introduced the category of abelian Hodge structures. It's a full subcategory of full tensor subcategory, yeah, of the category of polarizable Hodge structures. Well, here, in general, my hypothetical is not projective, so these Hodge structures are not polarizable in general. But still, I can consider some category of Hodge structures, well, generated by tori. Yeah, so let's put tori here. So this is a full tensor subcategory of rational Hodge structures generated by H1 of T. So T is a compact torus of some dimension. Okay, so these are kind of also abelian type Hodge structures, not necessarily polarizable, but still. And then, so here is what I want to explain. So this is, so let's phrase it just like this: that all cohomology, all these Hodge structures on cohomology groups of the hyperkähler manifold are abelian. Yeah, so the theorem. So this is so due to Nikon, myself, and Misha Verbitsky. So then we prove that so if X is an IHS manifold, then for all K, so this is abelian in the sense that it is in the subcategory generated by tori, and if X is projective, then of course this is in the subcategory generated by the abelian varieties. Okay, so yeah, so that's my goal today. So in the let me spend some time trying to explain the idea. So that is basically, so somehow this follows from the Kuga-Satake construction. Yeah, so any questions first about this? So the Kuga-Satake construction uses Clifford algebras. So let me again say a few words. So the idea of the proof. So that's so the last part will be the idea of the proof. So I will need to use the Clifford algebras. Yeah, so the idea, so in general, so what's the general idea that I have already mentioned, yeah? To understand these Hodge structures on the cohomology, we need to understand the cohomology groups as representations of these guys. So if we prove that they are, you know, as representations of these spin groups, they are contained in some representation somehow, if we construct the action of this spin group on some tori, and embed our cohomology groups into the well, into some tensor powers of this H1 of some tori on which this spin group acts, and prove that this is a morphism of representations, then this will imply what we want, because then the Hodge structures will be induced by this action. Yeah, so somehow the Hodge structure on the H1 of the tori should also be induced by the action of the spin group. So that's our goal somehow, to construct some well, you know, to replace this Hodge structure on H2 in particular by the Hodge structure on some torus. So where to find these torus? Well, let's recall a few things about the Clifford algebras. If anybody is following, someone is following the Misha's course, you are familiar, but I'll still, you know, fix the notation because I'm afraid that my notation is a bit different. So the Clifford algebras. I will use this V, yeah, with the quadratic form. So this is a quadratic vector space over Q. So let's say everything here works over Q the same way as over R, although there is no such thing as Bott periodicity here, I guess. Well, so the Clifford algebra is just the quotient of the tensor algebra of V, so the direct sum of all tensor powers of V. I think I should. They are not matrices or quaternions, so this is Q. So you don't have a. Yeah, okay, so let's not somehow think about this right now. So this is the quotient by some ideal. So the ideal will be, so the notation will be like this. So this J is generated by V tensor V minus Q of V times the unit. So I'll put this minus there, so this will be my convention. So for all V in my vector space. So a few things, so that I would like to introduce. So this, in other words, so when we have, so in this algebra, the Clifford algebra, when we have the square of some element, so in Clifford VQ, so it works like this. So V squared is equal to Q of V times the unit. And if we have UV, so U times V plus V times U, this will be equal to twice Q of UV, times the unit also. Let me introduce a few. So there are some involutions that I want to use. So first there is the parity. So let's define. So alpha of V1 times the product dot Vk. So this will be just minus 1 to the k. And beta of V1 dot Vk will be so minus 1 to the k times the same thing, So, and the beta will inverse the order of the factors. So this will, this is they are involutions on the tensor algebra, but they descend to Clifford. Because they preserve the ideal. So the composition, so for any A in Clifford, I will write A bar. So A bar will be the result of applying both things. So it will multiply by the parity of somehow the monomials by the parity, and also inverse the order in the product. So this is this somehow analog of complex conjugation. Since we have this parity, we have, so actually, so this is a parity involution. I will define the decomposition. So this Clifford has even and odd part. Clifford 0 and Clifford 1. So Z2 grading. And now, we'll be working with representations of the spin group, So I need to explain to you how to embed the spin group into the group of invertible elements of this Clifford algebra, So let's denote. So let's denote for brevity. So this Clifford VQ will be just C. So this curly C, let's just write curly C. C, just usual C was the value per it, so I'll use curly C. I want to embed the spin group into the group of invertible elements of this algebra. Invertible, multiplicatively invertible. So to do this, I will first, so in a few steps. Let's observe that, so what are the invertible elements? So let's observe that for any x in V such that Q of x is non-zero, we have that x is is invertible, So why? Because x squared will be Q of x times 1, so x inverse is equal to x divided by Q of x. So let's introduce the following group. So to introduce the group, so one other remark. So here in this tensor algebra, I of course have these summands, so the subspaces. So I may consider their projections. So I will embed V into the tensor into this direct sum. So there is this I equal to 1. It's just V. Yeah, and then I'll consider its projection. It does not intersect with the kernel, this V. Yeah, because this the definition of the ideal. So it is somehow because of this special form of this element, so it's easy to see that it does not intersect V. So V will actually project injectively into this Clifford. So we have a natural embedding of V into the Clifford of VQ, so into C. So this subspace. Now I want to introduce the group of elements of the invertible elements in C such that the adjoint action preserves this subspace, but the adjoint action twisted by this sign. So there are some subtleties because of the Z2 grading. So that's how I want to define somehow the twisted, the sign twisted adjoint action is defined like this. So you multiply from the left by the somehow alpha of x, and by x inverse from the right. So let's look at this group that preserves, so such that the adjoint action or the twisted adjoint action preserves the subspace. So let's observe what is this, what this twisted adjoint action, what it actually does if we apply an element, so this element here. So let's again assume that x is in V, q of x is not equal to, so I think I should use some other blackboard. Let's have a look. So if x is this element of the group C across, and let's say y is any other element. So let's try to compute this. So what is this? So this alpha of x is minus x times y times, well, x inverse, we know what it is. So this is x divided by q of x. And then, what is minus x times y? So minus x times y is y times x minus 2 times q of xy by this here relation, yeah? So, and then I multiply this by x and divide by q of x. And then I discover that actually, so then if I multiply x, I take the x squared, this is q of x, so this will cancel. And then in the end, I'll get y minus 2 q of xy divided by q of x, so that times x. So this is a reflection, yeah? So this is a reflection somehow in the plane orthogonal to x. A reflection. So actually we have a lot of elements in this group that act as reflections. So naturally also we may try to understand what this action preserves. So this action on V of this group, it preserves the quadratic form. That's actually also not difficult to see. So let's just have a look why it is true. So then, so if we have, so x is in this group G, and so y is in V, So Q of alpha of x, y, x inverse. This will be alpha of x, y, x inverse squared. Yeah, so then I need to multiply x inverse. So how to simplify this? So here, if I apply, so this is an element in V. So this is in V. So this is of degree 1. So if I apply alpha to it, it will multiply this thing by minus 1. So I can write this thing as follows. And then this will give. So alpha of y is also a multiplication by minus 1. So this minus 1 goes away. And then this is y. And then alpha of x inverse times alpha of x times y times x inverse, which will, in the end, so simplify to. So this is q of y. And x inverse will cancel. So this is q of y, right? So that's this action preserves the quadratic form. So this action, it defines the representation of my group in the orthogonal group. And this is already almost what I want. Because what I want is to construct the spin group, right? So the spin group is a double curve of SO V. And here I have already a representation. So we get a representation. So let's call it mu from G to the orthogonal group of VQ. And also, we have observed that we have a lot of elements that act as reflection. So this mu is surjective because its image contains all reflections. And there is a theorem that this orthogonal group is generated by reflections, actually. And the kernel of mu, so I won't compute this because I think so that I have, so you get the idea how these computations work. So in fact, it's not difficult to find this kernel. So the kernel are just the invertible scalars. So the kernel of mu is just, well, the Q star. Yeah, so our algebra is over Q. But it doesn't matter that it works over any field. Well, the kernel is quite big, but let's make it a bit smaller. So to make it a bit smaller, let's just define define the norm homomorphism from this G into, I guess, Q star again. So the norm will be just n of A is A times A bar. So this bar is what I have written, defined before. Okay, and so then the spin group is embedded as follows into the Clifford algebra. So the spin group is a connected component of the kernel of this norm homomorphism. So the definition is that so the kernel of this n is called pin. It has, it's not, well, I mean, so you may also somehow give these definitions properly, and then you'll see that these are not just groups of somehow abstract groups, but algebraic groups. And these are the groups of the rational points, actually. So, well, as an algebraic group, the spin is not connected, and you may consider its connected component just by intersecting with the even Clifford subalgebra. So the pin intersected with C0 is the spin group. So that's an explicit somehow embedding of the spin group into the Clifford algebra. And now we have the, of course, we have the, if we restrict this mu to the spin group, then this will give us the morphism onto SO VQ. And yeah, so because so here, if we intersect with this C0, so the elements there will be generated by even number of reflections. So what's the kernel of mu? The kernel, well, we need to consider the elements that go to that are in the kernel of this mu of norm 1, right? So these are just 1 and minus 1. So the kernel of mu is just plus minus 1. So this is our double covering. And now, okay, so that was somehow the first step. Well, this basically the definition of the Clifford algebra. Now, so back to the question. So how do we construct a complex torus? So we have actually on V our Hodge structure. We have a representation of the circle in our SOV tensor R that defines the Hodge structure. But then, so there is an observation. So this morphism defining the Hodge structure on H2 lifts to spin VQ. Well, I need to put this R here, yeah, to be precise. So this is tensor R, and here also, so the tensor R. Well, why does it lift? Well, let's observe this. It's actually indeed, so that's just the main somehow observation here to understand. It's not difficult. So this V tensor R, well, if we look at the Hodge decomposition, so what is V tensor R? So there are 2, 0 plus 0, 2, so they are complex subspaces, but we may consider the sum and then somehow intersect with, so take the real part. So this 2, 0 plus 0, 2 is a subspace defined over R. And then there is this 1, 1 part here. Okay, so let's just denote this for brevity by V plus R. Okay, so this is a two-dimensional vector space. How does the, well, my representation actually, so this action of U1, it fixes V11, so it doesn't act on this part. So it actually goes into a SO of VR plus, which is inside SO of V tensor R. But so this is also U1, right? And then, well, what is this map from U1 to U1? So the weight here is 2 and minus 2. So actually, so this is a double covering. So this is a double covering. Just because of the somehow, because it's type 2, 0 and 0, 2. So the action on these subspaces by multiplication z to the square and z to the power minus 2. So that means that this is a degree 2 covering. So actually, yeah, so and then what is this spin group? The spin group of this guy, well, the spin group is actually exactly also the circle, and the covering here is just the same map, essentially. So we may identify this U1 with the spin group. And then it lifts to the spin group somehow, yeah, by this identification. So more explicitly, we may say that the Clifford of V tensor R is the product of the Clifford of this VR plus and the Clifford of V11. So the Clifford of VR plus is a 4-dimensional algebra. So this is a 2-dimensional vector space. Then the Clifford will be just the degree 0 part, then VR plus and lambda 2 of VR plus. So this is of dimension 4. And the spin group is just somehow, so we have Clifford VR plus. Well, let's say that our VR plus is spanned by 2 elements, well, let's say EF. So this is the orthonormal basis. And then Clifford of VR plus, the even part is the span of E and the product EF. So this is the 2-dimensional vector space, and the spin group is a circle. So this is the circle in this R2. Well, and the map from this spin into SO VR plus is also the double covering. So essentially the same map. So we may lift this here into. So we may identify this with this spin VR plus, which maps here 2 to 1. Okay. So then, looking at this thing. So now, how do I want to define? So why do I want to lift this action? Well, now I will define the Hodge structure by this somehow identification. So now I have, so this spin VR plus is of course contained in the full spin group of my V. So we have, so there exists this lift rho tilde from U1 to spin V tensor R Q. And now how do I want to define this Hodge structure of weight 1 of the abelian variety? So let's look at this Clifford algebra. So this Clifford algebra of VR plus as a representation of this spin group. So here, so this R2 is just the standard representation of the circle. Okay, so and the Clifford 1 is just the 2 copies of the standard representation. So so this Clifford VR plus are the 2 copies of the standard representation. Well, and what about this whole thing, so the Clifford? So if I take the tensor product as a representation of that U1, so this U1 does not act on this space. So it will be just several copies. So the number of copies is determined by the dimension of this thing. So the Clifford algebra somehow as a vector space, this V tensor R Q is a direct sum of standard representations of U1, which is this spin VR plus. Okay. So if I use now this action of U1 on this space to define the Hodge structure on it, so the standard representation means what? Means that if I complexify this thing, the weights will be 1 and minus 1. So this standard representation is essentially as a Hodge structure. It is a Hodge structure of an elliptic curve. And this will be so somehow well, but this thing is not defined over Q. This thing is something defined over Q tensor R. But still, so the Hodge type will be the same. So as the Hodge structure, this will be. So let's denote this by H, this Clifford algebra of VQ. then H tensor C will be the Hodge structure of a torus. So it will be of weight 1. And this is my Kuga-Satake, essentially this is the Kuga-Satake construction. So this is the definition of the torus. Well, it's not a torus, of course. It's just the rational vector space that should be the rational cohomology of the torus. The torus itself is not canonically defined. There will be only this rational Hodge structure of weight 1. Yeah, so this is the object in the category of Hodge structures generated by tori. Yeah. And now, well, so this is my Hodge structure. Now, the thing I want to do is somehow to define the embedding. Embedding of my original Hodge structure, which was V, somehow into this H, or into something generated by H. So V was of weight 2, so this H is of weight 1. Well, actually, I will construct an embedding into the second exterior power of H dual. Well, H and H dual are the same thing as spin representations, but it's just a bit more convenient to work with H dual. So I'll explain now this embedding. Okay, so this is the definition of the Hodge structure. Now let's construct the embedding. The embedding of V into yeah, so okay, so I want to, so there is a bit confusion with weights. So actually, okay. So since I want to, so it will be a bit easier to write down an embedding in lambda 2 of H dual. So actually I want to, so when I define the Hodge structure, since I have only this action of the circle, it does not actually define the weight, it defines only the Hodge decomposition. So I can actually put, let's put weight -1 on this Hodge structure. And then H dual will be of weight 1, and I want to construct an embedding into lambda 2 of H dual, like this. So this is of weight 2, and this will also be of weight 2. So how to construct the embedding? Again, so just the idea. To construct the embedding, we should use some bilinear form on the Clifford algebra. So recall that so the bilinear form on the Clifford algebra, I'll just write this down. So there exists non-degenerate pairing I'll denote it by tau. So C was the Clifford algebra. So C tensor C goes to Q. So how does this pairing work? So tau of xy will be equal to the trace of x y bar. So the trace here is the trace of this element as an endomorphism. So this is an element of the Clifford algebra. So this element is considered as an endomorphism of the Clifford algebra itself when the algebra acts on itself by left multiplication. So acts on C by left multiplication. So this trace is the trace of this endomorphism. Well, and then this it turns out that this tau, so it is non-degenerate, and then there are a few other properties. I'll just write them down. So these are the same type of computations that we have seen already, so I won't do them. It's easy to check all this. So so actually this tau is spin invariant in the sense that if I somehow for any A in the pin group, tau of AX, AY is equal to tau of XY, non-degenerate, and so, and analogously, actually, I may define the same thing on the direct sum of any number of copies of this Clifford algebra. I'll do this a little bit later. So now, so let me define this embedding first. Or maybe, so somehow, so let me write first. So that analogously, on H, so for H, I want to take several copies, direct sum of several copies of this C. We have the tau on this H. And then, so I'll use this H, so that is, again, so that's the direct sum of several copies of this Hodge structure of abelian type. So how do I construct the embedding? So given any element in V, let us define the following skew-symmetric form. So this tau was symmetric, but now I want to twist it. So let us define omega x as follows. So this is tau of x uv. And then one checks so easily that omega x of uv is equal to minus omega x of vu. So this omega x is the skew-symmetric form. So this is in lambda 2 of h dual. And this is my embedding, actually. So now, this defines somehow phi from v to lambda 2 of h dual by sending x to this omega x. Okay. So once again, so x was an element of my original vector space V. So then I take the Clifford algebra of this V and take its several copies, direct sum of several copies, and use some canonical pairing, non-degenerate pairing, on this H called tau. So it was symmetric, but then I twisted by x. So it will become skew-symmetric. Basically, it will become skew-symmetric because of this property, because of this bar that appears here. So this gives an embedding, actually. So it's easy to see that this omega x is never 0 if x was not 0. And actually, it's a morphism of, well, everything here is canonical. So you see this tau is spin invariant. So everything actually is compatible with representations of the spin group. So phi is a morphism of spin representations. Well, that is already the end of the story for a K3 surface, because for a K3 surface, so this is all. So as I said, so the Hodge structure on this V is induced by the action of the spin group, as well as the Hodge structure on this H. Yeah, so by construction, it is just induced by the spin group action, and so this will give you a morphism of Hodge structures. So this phi is a morphism Hodge structures. For our hyperkähler manifolds, we need to work more. So for hyperkähler manifolds, we need somehow to enhance this construction a little bit. It works as follows. So the next step. So now, V was the H2. So how to embed all cohomology groups of a hyperkähler manifold? So all cohomology groups were the representation of the spin group, but of a bigger spin group. So you remember there was this Mukai extension of V, and the cohomology ring was the representation of the spin group of this Mukai extension. So now we need to somehow enhance this construction and construct analogously somehow an embedding of representations of this extended spin group. So let's do this.
So quick question, what is the role of M?
Yeah, so M, so far it has no role, but it will have. So yeah, you're right. Actually, for RK3 surface, I could just take M equal to 1. Everything fine. But now I'll need this M, so I have introduced this in advance because I'll use it. Well, so well, I want to introduce here some notation. So let's denote the dimension of this H. Okay, so the Clifford algebra, the dimension of the Clifford algebra is the power of 2, and it will be divisible by 4 unless the space V was one-dimensional. So I'll just write this as 4 times n for some n. And so I'll look at this embedding. So let's denote its image by W. So I have the image of phi is W. Huh? Okay. Divisible by 4 unless it is 2-dimensional, which is the case only when the space was 1-dimensional. Now, okay, so let's look at this. So I hope to now that you'll see this analogy with this Fujiki relation that I have shown. So look, this lambda 2 of H star is the cohomology, second cohomology of some torus, right? And we have these guys, so omega x. So they're called omega x because they kind of look like Kähler forms on a hyperkähler manifold. So let's consider the following polynomial. So this W is the image of the embedding. So let's consider the polynomial on this space, a polynomial of degree 2n of W star. So the P of omega is equal to omega 2n, right? So, yeah. So this is in lambda 4n of W dual, which I identify with the rational. Sorry, of H dual. Yeah. Okay. Actually, I could have written here as well H dual. It's not so important, but then I will restrict it to W. So this polynomial function on this vector space. It is invariant under the action of the spin group as well. So let's see. So this H, so there is this spin group action, and so this is the morphism of my of my spin representations. So this is a sub spin representation here. So this W. So if I restrict this polynomial, yeah, to W. So why is it invariant? Well, because taking the exterior power defines a morphism of spin modules, and this spin module is trivial. So this is one-dimensional. So this polynomial is actually a spin VQ invariant, right? Well, this W is isomorphic to the representation of spin given by the adjoint action, so that this is the standard representation of SO. So actually, the classical invariant theory implies that this polynomial is actually a power of the quadratic form. So on this representation, so there is, or on the on this vector space, the only spin invariant polynomials are powers of the quadratic form, actually. So this P is equal to, well, let's say some constant times the power of the quadratic form. So this is very similar, yeah, so to the Fujiki relation. So this P of omega is omega to the power 2n, and this is equal to A times Q of omega to the power n. So this is kind of Fujiki relation in this purely linear setting. So if you think about this Fujiki relation, then it is not somehow surprising that, in fact, we also have this extended group action. So we have the, so let me recall the Lie algebra of the Mukai extension. It was, well, V in degree -2, then there was SO V plus some, well, let's say, so the degree 0 part, and plus V in degree 2. So here we had the dual Lefschetz operators, and here we had the Lefschetz operators. Let's define the action of this algebra on the exterior algebra of H. Yeah, so well, if we have some element in the exterior algebra of H dual, let us define, and well, X. So this X was an element of V. So then Lx eta will be omega X wedge product eta, and lambda X eta will be omega X contraction with eta. So once again, so those omega X was, so what is omega X? That is how I define this embedding. Yeah, so phi from V to lambda 2 H dual, it sends X into the omega X. So this is my embedding. And then I use this omega X to multiply. So the exterior multiplication by the elements of this algebra. And the dual. And then the proposition is that, so this defines an action. Yeah? So this star defines SOV tilde Q tilde representation on lambda H dual. Well, it integrates to the representation of the spin group, so the corresponding spin V tilde Q tilde representation is faithful. Okay, so so this rule defines an action of this algebra, and the reason is that, well, I mean, it's not the reason, but somehow there is some parallel. This story is parallel to the classical story for hyperkähler manifolds. So when we have this Fujiki relation, then somehow we have this algebra action, and it works here in this linear setting as well, and it is much easier, of course, because it's a pure linear algebra. So you can just check. It's a computation which is not so difficult, that you may define the action of this algebra on this exterior algebra of H dual. And check that so this is the faithful spin representation. So this spin acts on this space without without the kernel. Well, now what will we do? Well, our cohomology. Yeah. So the conclusion. The conclusion is the following, actually. So let's observe that for any SO V tilde Q tilde representation U, there is M such that for H equal to C tens direct sum M times. U is contained in lambda H dual. Why is this? So as SO V tilde Q tilde subrepresentation. It's just because this thing is a faithful. You know, if I take H equal to C, so just start from M equal to 1. We know that actually all representations. So we have discussed this theorem. That if I have some faithful representation of a reductive group, so this is a reductive group now, then all its representations are contained in the tensor algebra. So in this case, so the representations are self-dual actually. So I may consider just the tensor powers. Yeah. So so this U is contained in the direct sum of tensor powers of this lambda C dual. Yeah, so this tensor power is isomorphic to the exterior algebra of the several copies of C dual. And so if I choose this I big enough, so if I choose this, so there exists such M such that any representation is contained in this guy. So that's the role of this M. So that is why I want to actually allow arbitrary direct sums here. Okay, so once again, so the conclusion is what? So if I have any representation of this SO, I may embed it into some representation of this type, where H is the direct sum of several copies of the Clifford algebra. And my cohomology was a representation. Yeah, so that's the LLV theorem. So if I take U equal to the cohomology ring, of X, I'll get an embedding of, let's say spin V tilde Q tilde representations H X Q into this exterior algebra, and this is the cohomology of a torus. Yeah, so the torus somehow is well, I take this H is a vector space, a pure vector space. I can choose some lattice there, take the quotient. This will give me a torus, a complex torus. And then the exterior algebra is the cohomology of the torus, the total, the cohomology ring of the torus. And as I said, so the Hodge structures are induced by this spin group action. Well, actually by the smaller spin group action, which is a subgroup here. So the Hodge structures are induced by the action of this smaller guy. So this is an embedding of Hodge structures. It's not an embedding of rings, yeah, so it's an embedding of Hodge structures. And also, well, so far I have not said anything about why this Hodge structure will be polarized, and I think I won't say anything. So let me just so mention that you may prove it's not difficult also that actually when H2, so when this V, the Hodge structure was polarizable, so that there was some rational positive 1-1 class in V, then actually H is also polarizable. The polarization is essentially produced using the same trace form, but with some twists again. So you may prove that this will be the Hodge structure of an abelian variety, in fact, when X is projective. So then this concludes the proof, and this shows that all these Hodge structures on the cohomology of X are abelian. Okay. Yeah, so any questions, comments? So I think, yes, so that's a good point to stop. So thank you very much for attending. And yeah, thanks.